Okay, so we're on to section 11.2 now. And so this is a probability of involving not or events. So let's look at, don't seem to have that many assigned, but I may change that. We'll see. Okay, so we're going to do problems 4 through 9, which is one group of problems. Probability for rolling a die. This is for the experiment of rolling a single fair die. Find the probability of each event. So what we really have to do is just interpret what they're asking for here. So number 4 says not less than 2. Okay, so what does that mean? Not less than 2. It means, can 2 be included? And the answer is yes, because 2 is not less than 2. So the other choices, the rolls of a die that are not less than 2 are 2, 3, 4, 5, and 6. That's 5. So the probability of not less than 2 is going to be equal to 5, because there are 5 of the 6 possible are not less than 2 out of the 6. So there's a probability of 5, 6. Okay, number 5 says not prime. So there's 2 ways of looking at it. You can do, I'll just tell you both ways. One is you can just, again, look at the numbers. And so here are the numbers on the die. So which ones are not prime? Well, 1 is not a prime number. 4 is not a prime number, and 6 is not a prime number. So the probability of not prime is going to be the number of things that are not prime divided by the total number of possibilities, which is 1/2. Now the other way would be to take the probability of being prime, which is equal to also 3 out of 6, because 2, 3, and 5 are primes, and that's 1/2. And so the probability of being not a prime is equal to 1 minus the probability of being prime. And you get 1 minus 1/2, which is 1/2. So there's the direct way, or there's the indirect way. Okay. So the next one we have is odd or less than 5. So again, we'll list all the possibilities here, and then we'll ask the question. So those are the 6 possibilities, and it says the probability that it is odd. So we'll get rid of those 3. And not prime. So this is not prime. This is not prime. So it only leaves us with 1. So the or means it's 1 or the other. So we take them all into account. So, well, actually, going the other way around here. So they're asking, is it odd or not prime? So actually I've marked through 5 of them. So I've counted 5. So there are 5 that are odd or not prime. So again, that's the numerator. So the probability of what we just talked about is going to be the number of occurrences divided by the total number of possibilities. The next one is even or prime. So we'll do the same thing. So it's even or prime. So 2, 4, and 6 are even, 3 and 5 are prime. So that's, again, 5 out of the 6 that I've marked through, I'm counting. mark through is not eliminating, but they're counting those. I should have circled them instead of marking through. So there are 5 that are even or prime. So the probability of that occurring is, again, 5 out of the 6, or 5, 6. And again, both of these, I could have done the opposite. I could have said, what's the opposite of odd and not prime? Well, even and prime. Is that right? Are not, they're even and, well, actually, it's not quite as simple as that, is it, with the or statement. So let's just keep doing what we're doing. Number 8 says odd or even. Again, these are the possibilities. I'm going to circle them this time instead of marking through them. So odd, even, so we pick all 6 of them. So the probability of being odd or even is 6 out of 6, which is 1. Now if we said odd and even, there'd be no. The probability of being both odd and even is not possible. And then the last one is less than 3 or greater than 4. So what numbers, again, we're going to mark, just list them, and we do one, and then we do the next, and the total number we have circled is the or. So less than 3. These 2 are less than 3. These 2 are greater than 4, so that's 4. So the probability of that statement occurring is going to be 4 out of 6, which is 2/3. Simplified down. Okay, now I think we've done the next group in class. And what I have next on my list, 26 through 31. So 22, I'm just thinking about them doing some other ones besides that. 22, we'll probably talk about that in class. So I think I'm gonna, let's see what we got left here in this section. We don't have a huge amount left to do. What I'm trying to do is avoid things that you have to have taken the first semester to know how to do, and that may be why I am skipping over those, because I don't want. We'll also do 34. So we'll do 26 through 31 and 34. Okay, so the next 3 groups are, or the next grouping is asking some questions. So if the table gives golfer Brian Donahue's probability of scoring in various ranges on a par 70 course in a given round, find the probability of each of the events. So you can see I've got listed the probability of each one of those occurring between those events, and if you add all those up, you should get 1. 0.04 plus 0.06, etc., etc. You add those up, and you should get 1. So I'm just going to confirm that's true, or they screwed something up. Okay, 0.04 plus 0.06 plus 0.14 plus 0.3 plus 0.23 plus 0.09 plus 0.06 plus 0.04 plus 0.03 plus 0.01, and you get 1. Okay, so and it has to be that way, because if you're below 60, that covers everything below 60, and if you're 100 above, then that covers that as well. Okay, so now we just answer the questions, and really all you have to do is just add up the probabilities. The total probability is the sum of each one. So it's kind of like an OR thing, 95 or higher You do the ones that are 95 to 99 and the ones from 100 or above. So 26, we add two of the probabilities together. We take 95 to 99, which has 0.03, and we take 100 or above, and we add those two together, and you would get 0.04. Likewise, 27 par. Par is 70. So par or above, that means it's going to be 70 to 74, 75 to 79, 80 to 84. And we'll show you the two ways to do it here. Get the same answer, but it just shows how it works from a complementary standpoint. So each one of these has some value. So we get 0.30, 0.23, 0.09, 0.06, 0.04, 0.03, 0.01. You add all those things together. 0.3 plus 0.23 plus 0.09 plus 0.06 plus 0.04 plus 0.03 plus 0.01, and you get 0.73. So the answer is 0.73. Well, actually, did I make a mistake? Because I'm not getting the answer in the book. Oh yeah, I made a mistake. I didn't put 0.23 in there. I put 0.2. Okay, 0.76. Now, the other way of doing this is to find the probability of less than par. So what that would be is it would be the probability of below 60 plus the probability of 60 to 64 plus the probability of 65 to 69. So you add those together, which is 0.04 plus 0.06 plus 0.14, and you get 0.24. So the probability of 70 or greater, which is the opposite of less than par, you just take 1 minus the probability less than par. So you get 1 minus 0.24, which is 0.76, and get the same answer. This one might be preferred because you have less numbers to add together. Okay, in the 80s. So what we do there is we take the probability from 80 to 84 plus the probability of 85 to 89, which is 0.09 plus 0.06, which is 0.15. 29 is less than 90. So in this case, I'm going to use the opposite, which is 90 or greater. That's the opposite of less than 90. So the probability of 90 or greater is going to be the probability of 90 to 94 plus the probability of 95 to 99 plus the probability of greater than 100. That's going to be 0.04 plus 0.03 plus 0.01, which is 0.08. And so the probability of less than 90 is equal to 1 minus the probability of greater than or equal to 90. Same thing as that. So you take 1 minus 0.08 and you get 0.92. Okay, number 30. Not in the 70s, 80s, or 90s. Probability of not 70s, 80s, or 90s. So again, that's going to be a lot. So the opposite of that is the probability of, so the opposite is going to be the probabilities is less than 60. Less than 60, 60s, greater than 100. Because this I have to add 6 things together. This I only have to add 4 things together. Yeah. So I mean it's 6 one, a half dozen the other. So either way, you can either do this or you can take 1 minus that. And let's just hopefully at this point I'm not going to write everything out, but what we'll do is we'll add the ones in the 70s, 80s, and 90s. So that's 0.3 plus 0.23 plus 0.09 plus 0.06 plus 0.04 plus 0.03. So if I do this, the probability of being in this, well, yeah, and actually these are actually the same thing. Probability of not being in the 70s, 80s, and 90s is the same as the probability of being in the 60s and above 100. Or we could do the opposite. We could take the probability of being in the 70s, 80s, and 90s and subtract that from 1. So these actually should give us, these are actually saying the same thing. It's not really opposite, because I was thinking about it differently. So these two are the same. So let's just do this. Like I said, they're answering the same question. So what we do is we take 60 and below, add that to the 2 cases in the 60s, plus greater than 100, which would be 0.01. And we add those together, you get this plus that is 0.2, 0.24, 0.25, 0.25. Okay, so that's the probability. Now if you looked at the opposite of not in the 70s and 80s, you could do it in the 70s and 80s and 90s, 70s, 80s, 90s. In that case, you would add the other numbers up, the ones we haven't added up already. So those 6 ones, 2 in the 70s, 2 in the 80s, 2 in the 90s, 0.3 plus 0.23 plus 0.09 plus 0.06 plus 0.04 plus 0.03, you get 0.75. So the probability of not 70s, 80s, 90s equals 1 minus the probability in the 70s, 80s, 90s. And so you get 1 minus 0.75, which is 0.25. So this answer is the same as that answer. And then the last one I asked is about odds. What are the odds of Brian scoring below par? So the way you do that is you're going to, its odds are favorable to unfavorable. So it's favorable to unfavorable. So we can do that in terms of probability. So the number favorable is below par, and below par would be everything in the 60s and less. So that's going to be 0.014 plus 0.06 plus 0.04, and that's going to be 2. The rest, which is actually going to be 1 minus whatever I got here. So I'll have add those together. You get 0.24. 1 minus that number is 0.76. Now you can multiply those by 100, so you get 24 to 76, but you should be able to simplify that. So if you divide both by 2, you'll get 12 to 38. Divide by 2 again, and you'll get 6 to 19. That's your answer. You always want to put that in simplest terms by making sure that you can't divide both numbers by a common factor. And then the last problem is 34, and it says comparing empirical and theoretical probabilities for rolling dice. Roll a pair of dice 50 times, keeping track of the number of times the sum is greater than 3, is less than 3, or greater than 9. So it's 2, 10, 11, and 12. From your results, calculate the empirical probability for the event less than 3 or greater than 9. So you have to, we don't know what the answer is, so we're just going to have to set it up as a theoretical statement. So the probability of less than 3 or greater than 9, and that's going to be the number of times we get 2, 10, 11, or 12 divided by the total number of times we rolled the dice. So that will be our empirical probability. Now the theoretical probability is, and again it doesn't, we don't know until we actually do the result. Well, actually it tells us to do it. Okay. So we actually have to roll the die, which we haven't. You might not have a die. So I'd have to actually run the experiment, which I'm not. I haven't. So what we would do is you'd roll the die 50 times, you'd record the number, the sum, you'd come up with a table, you'd add these numbers together however many times this occurred, and then you would compare that with theoretical probability. And if we go back to a previous problem, the probability of getting 2 was 1 out of 36. And the probability of getting 12 was 1 out of 36. And the probability of getting 11 was 2 out of 36. And the probability of getting a 10 was 3 out of 36. And so if you add all those together, you get 3 plus 2 is 5. 5 plus 2 is 7. You get 8 out of 36, which is 2 out of 9. So if you divide both by 4, you get 2 9. So that's the theoretical probability of getting this, and then you would take your actual experimental results and compare with that. And, you know, the more dice you roll, the more likely, and as long as you have a fair dice, the more closely this experiment comes to actual fruition or matches up.